Up next on the Dynamical Systems playlist is modern topics in dynamical systems. Okay, so our goal here is to connect advanced theory of dynamical systems to modern scientific research. This lesson covers random dynamical systems, delay differential equations, coupled oscillators, network dynamics, control and synchronization, and of course we have the prerequisites. Of course, it is expected that you should be familiar with ordinary differential equations, which is properly covered on my channel right here. So you want to check that out. I have a whole playlist on ordinary differential equations. So if you want to check that out, you have all of that here. So you just come to my channel and you know, then you can check playlists and you find everything there well treated. Ordinary differential equations, where is it now? Somewhere close. Yeah. So you have ordinary differential equations there. But if you want to look at differential equations in general, I have 87 videos covering ordinary, partial, Laplace, even some numerical methods. Okay, that's a prerequisite. Another one is linear algebra, which I just finished teaching, not quite long. So that's the playlist I finished before coming to dynamical systems. So if you need to know anything about, if you want to know linear algebra, you have it all here. And then basic probability, of course, I have it covered too. I have probability treated a long time ago. I think it's somewhere close by. Yeah. So I have 17 videos covering different aspects of probability you can imagine. Then, as the numerical methods too. I have a whole playlist on numerical methods, or I think I called it numerical analysis. Yeah, numerical analysis. Um, where is it now? Numerical analysis. I have 55 videos, I think, on numerical analysis. It should be somewhere close by. Okay, I think it came before. Yeah, I have 78 videos, in fact, on numerical analysis right here. So you want to see different aspects of numerical analysis. Then, of course, Python, talking about NumPy, Matplotlib. Yeah, I have different videos related to Python. So I think the very first set of videos I did on Python must have been on what I called scientific computing. Where is that now? Scientific computing. That came. Yeah, I have 19 videos. I think it's a playlist I'm still building. I abandoned it a long time, so I think I should get back to it. But beyond that, I also have specific videos on Python. For instance, in fact, the most important one, if I may recommend, is Python Basic with JD. So it takes you from, like, if you have never done anything with Python before, you can just come to this playlist and get the whole idea from what Python is, how it was, who made Python, how did it start, what does it do, and then you go step by step. Of course, I have some Python related videos like, machine learning with Python, of course, data analysis, SQL, and all of these things. So all the prerequisites are properly covered on my playlist for sure, on my channel. So recommended background, of course, you need a background in chaos theory and stability analysis, which I've already treated in this particular playlist on dynamical systems. So let's go ahead and talk about the very first topic. Modern topic in dynamical system. That's talking about random dynamical systems. Okay, so random dynamical systems include stochastic effects. So you have general stochastic differential equation dx equals f of x comma t dt plus g of x comma t dw of t, where dw sub t rather, where w sub t is Brownian motion because we're talking about random, right? So the idea of randomness there. So we have, Brownian motion is random motion. Then you have g of x comma t, which is the noise strength. So you have dynamical system with noise in it. These are called stochastic differential equations, as you can see. So we have noise right captured right there. So you have applications of random dynamical systems in climate modeling, financial systems, population biology, neural activity, and chemical reactions. Noise can induce transitions, stabilize unstable states, or destroy order. Okay, so noise can destroy order, stabilize unstable states, and of course, induce transitions. Then you have an example of that like in this stochastic logistic equation where, we've been dealing with logistic equation all this while, which is Rx into 1 minus X for the most part, where we can, where whatever R is determines the how chaotic or non-chaotic the system may be. So, but in this case now, you have a stochastic logistic equation, and that is dx equals R of X into 1 minus X dt plus sigma X d omega dw sub t, where R is the growth rate as usual, and it determines whether the system is chaotic or not normally, and sigma is noise in this case. So this models random environmental fluctuations. Okay, and then I mean, to see what that looks like, we have the a stochastic simulation with that kind of system right there. So you see, we import NumPy, we have matplotlib also, NumPy for numerical Python, matplotlib for plotting. Then we have we use R to be 2.0 here, and sigma is 0.3. T is 10, dt is 0.01. So we can vary these values to see the different behaviors of the system. And of course, did you have N is the number of iterations for sure, and that's T divided by dt. That's 10 divided by dt. That's more like two zeros, right? That's 10,000. That's like 1,000 iterations right there. Then for I in range, we deal with the noise part, and that's what you have. And then that returns xi, which is x plus r. So the logistic equation itself right here, starting with the initial condition, I believe, and then you have the logistic part and you have the noise part like that. So yeah, so we run this and you see what this actually does look like. So the function itself has been declared here, having taken care of every other aspect. So see what happens here. So this is the stochastic logistic growth. This is how this looks like. Okay, now what if I make this 4? Now when you go to 4, the whole thing is already going chaotic normally. Okay, I mean, we have other things, the noise combining with it to make it behave in a certain way. Okay, so what if I keep this as 2, and then this one is now like maybe 1.0 even. Okay, then I do this, see what it looks like. So you have all of these things going on right there. So that noise has certain impacts on it. Okay, so let's leave that alone. Haven't talked about it. So then we connected research topics to the idea of random dynamical systems, right? We've seen some applications. So of course we have research topics that may be talking about random attractors, noise induced bifurcations, stochastic resonance, and large deviation theory. So if you want to take up any of these aspects, then we go ahead to the next modern topic in dynamical systems as it relates to delay differential equations. Delay differential equations depend on past states. Okay, so you try to look at the current state based by considering the past state, right? So the general form is the x dt. Okay, I like to make this bigger by just adding a d to it, and that makes it look bigger. Like what you have now, the x dt is f into x of t comma x into t minus tau. So this t minus tau, this tau is the delay, where tau is the delay, right? So instead of, you have x of t in time, and then you have x of t at a time tau less than the current time. Okay, so and you have applications of delay differential equations in things like gene regulation, epidemiology, traffic systems, engineering feedback loops, and neural networks. So delays often cause oscillations and instability. Okay, so delays cause oscillations and instability. So we have a very good example here. We have a delay. So it's more like we have everything for logistic equation, right? So this is a delay logistic equation where you have x of t dot to be equal to rx into 1 minus x, but x now is a function of t minus tau. And so delays can destabilize steady states. That's one thing we see. So delay can bring some randomness into a system. So look at what we have right here. So like what we had before, R is 2, tau is 1. So 1 is the delay now. So the time step delay is 1. Then the t is 0.001. T is 20. And we have all of this. Then we define the function itself now. So we have the delay steps and all that. So if you run this now, see what this looks like. So this is what the delay logistic model looks like. So what if we make this normally to have some to increase it's chaos level. So you have this now. So instead of being that chaotic, you have, because of the delay now, it's like this. What if our tau is 2, which is the delay time itself? Okay, yeah, see what that looks like. So we have some impact like that. So let me take it back to what it was originally, and then we have the delay stuff like this. So I think the declaration here really is important, like this. Okay, so we can have a delay differential equations, which and like we said, delays can destabilize steady states. Now we have research topics in that line of delay, which is we have things like delay-induced chaos, distributed delays, control with delays, and neural delay models. So then we go ahead to talk about coupled oscillators. So that's another new topic, modern topic in dynamical system. So we talk about coupled oscillators. So coupled oscillators interact through phase or amplitude. Okay, they interact through phase or amplitude. The general form is theta I dot, which is omega I plus summation along j of kij sine theta j minus theta I. So that's talking about coupled oscillators now. So, and a very good example of that is the Kuramoto model. So, which is theta I dot equals omega I plus k over n summation from j equals 1 to n of sine theta j minus theta I. This model studies synchronization. So, and then you have the other parameter r equals absolute value of 1 over n into summation from j equals 1 to n of e I theta sub j. Okay. And the interpretation is that for r approximately 0, we have incoherent. And then for r approximately 1, we have synchronized. Okay. So it's either synchronized or incoherent, depending on the approximate value of r. So this is the Python code to deal with that, the Kuramoto simulation now. So here you have, of course, the values n, k, dt, and t, and then you have the omega, you have theta, which introduces a measure of randomness into the whole system. And then apart from that now, you have so you have the steps here, and then for everything in range of steps now, for the coupling, you have sine. So you have theta, uh, the first theta minus the second theta, and then theta plus. So it's like we are updating the theta. So that's dt into omega plus k over n coupling. That's from the system where we're given like this particular one. This should be theta I dt. So dt now is coming to multiply this whole thing. And that's how you can see dt into omega plus k over n coupling. Okay, so because from this theta I dot now, so theta I dot means the theta I dt. So dt multiplies this whole thing, and this whole thing is what we call the coupling here, because this is coupling, and the coupling has been defined here like the summation of all the theta theta I minus theta j, like that. So, and by the time we run all that, we see what the coupling looks like, and this is exactly what that is here. So for synchronization in that situation. Okay, so that is what we got there. So we move on to research topics in this area of the new topic about coupled oscillators. And then we have things like chimera states, adaptive networks, explosive synchronization, and power grid stability. Another new topic, modern topic in in dynamical systems is about network dynamics. So there are dynamics on networks. So you have xi dot equals f of xi plus summation along across j of aij, g of xj, comma xi. So where A now is the adjacency matrix. I've talked about the adjacency matrix first time under, I have a playlist, right? Talking about network, graph and network theory. Let me see what that is like. Where is that now? That was a long time ago, relatively long. Um, Network and graph theory. Okay, yeah, this is it here. 25 videos covering graph and network theory like that. Okay, so you can understand the idea of networks and adjacency matrix and all that. So adjacency matrix is the matrix of a network, right? So, and then we talk about diffusion on networks. Like you can have, of course, when you talk about things like epidemiology and everything, they can spread. They've spread according to how on networks, like they spread among people who are connected. So you have x dot equals minus lx. So L is the Laplacian matrix here. This models consensus and diffusion. So we have is we have Python code to demonstrate that kind of idea. So you have the network diffusion. So G here you have nx.erdos. So you see, this network X library is the Python library for dealing with networks. And if you check that playlist on networks, you see all of how all of that were demonstrated a lot there. So you talk about the Laplacian, the Erdos-Renyi graph, and things like that. So, and then we just run this now, and you see what that looks like. Okay, so we have the consensus states, from along the X and Y axis like that. So you just have them spread over here. So you have things happening on networks. Okay, so you have research topics related to that. Things like multi-layer networks, temporal networks, epidemic spreading, and network controllability. Like I know one of the important textbooks I recommend on network theory is there's I think this there's this book on network epidemiology by uh, Naoki Matsuda, I believe. Network epidemiology. Network epidemiology. Okay. So, yeah, I think this is the book here. I suspect this is the book. I want to believe this is it. Oh, this is, yeah, okay, this is by another author. But of course, this particular one I'm talking about is, I think, Network Epidemiology by Naoki Masuda, and some other author like that. So, okay, let me just add Masuda to it. So maybe I can get the specific book. Yeah, Temporal Network Epidemiology. Yeah, this particular book by Naoki Masuda and Peter Holm, right? So I think it's an excellent book if you're considering temporal network epidemiology, how epidemics spread. This book covers recent developments in epidemic process models and related data on temporally varying networks. So, like temporal talks about time, right? Time network epidemiology, if you like. Okay, so that's one excellent book on. If you are interested in how epidemics spread on networks. You want to check that out. Then I come to another modern topic talking about control and synchronization. So you have a controlled system, x dot equals f of x plus bu. So u is the control input. So this term now adds a measure of control. So you can add control to a system to regulate it sort of. So you have control methods like feedback control, optimal control. Yeah, I'm into optimal control because we get to use optimal control on the spread of diseases and things like that. Then there's spinning control and robust control. So, and imagine we have the usual Lorentz system. That's x dot y dot z dot all this expression. And then you can add a feedback to it, which is the control where u is equal to minus kx. All right. So now you see this on x now. So this adds a measure of control. Now let's see the impact that has. If you now have the control, we've seen the Lorentz system that it is quite a chaotic one. But now adding a control, what happens? What does that do? Okay, so we have NumPy, matplotlib as usual. So sigma, rho, and beta, these are the standard values of these things. And then now, because we introduce this measure minus kx, so let's say k is 5. Okay, that's the control measure. We can vary that to see what the impact it has. So we have dt to be 0.01, t is 20, n is the integer value of, you have t divided by dt. Okay, we have t divided by dt. If it is not integer, you just take the integer value of that. And then for u in range this, you calculate minus k times x. Then you have all the dx, dy, dz. And then you have to update x plus or minus dx dt, y plus or minus dy dt, z plus or minus dz dt, and so you see the u is added to the system now. So plus u, which is minus kx. So that's the control to it. So if you run this, let's see the impact this has on the Lorentz. We already know the Lorentz thing to be a very chaotic one. In fact, you have, the chaos is so serious that, you have two branches or something like that, depending on some values like that. So what if I increase the control to 50? The K value of to 50. Okay, see what happens. So the control is stronger in this case, right? So you can actually add control to a system to contain it as much as possible. If I make it 200, what do I get? Okay. Okay, see what happens here. Okay, the control becomes more and more serious. Um, okay, so initially we had it to be 2, I believe. Yeah, this is what it looks like if it is 2. So yeah, you can control a system like that. Okay, the original thing was 20, right? So this is what that gives us. So it depends on the level of control you want. So we talk about synchronization control. We have a master slave systems like this. So x dot is f of x and y dot is f of y plus k into x minus y. And the goal is to ensure that the norm of x minus y approaches zero. Okay. So and we have research topics in this regard, talking about controls in this system, that's talking about control and synchronization. All right. So we have some research topics that you may want to consider, like pinning control, event triggered control, secure communication, distributed control. So at the end of the day, we talk about the unified research perspective. For random dynamical system, the main question is the role of noise in a system, and the modern focus is climate tipping. Then different delay differential equation, the main question is the role of memory, and we can use that in brain modeling, right? So how memory affects a human being or something. Then we have oscillators now. The main question is about synchronization in power systems, for instance. Then we talk about networks. Here want to study structure effects, and the modern focus is on AI graphs and control in steering systems, and the modern focus is on smart tech. Okay, like self-driving cars and things like that. So you can consider suggested research projects for different level of experience, right? For a beginner, you can look at things around noise and stability, delay oscillations, Kuramoto transition, and intermediate, you can look at epidemics on networks, pinning control, adaptive synchronization, and advanced. You can look at random attractors, multilayer networks, and chaotic control. So some mathematical tools necessary for all this. You can master Lyapunov theory, which I've dealt with amply in this playlist, bifurcation analysis, spectral graph theory, stochastic calculus, and PDE methods. Well, I have a playlist on partial differential equations. It's all what I added up to have differential equations. So they have partial differential equations there, 27 videos. Oh, they are still part of this too. Then when you talk about numerical analysis, I have different methods there to handle partial differential equations too. Where's that video on numerical and the playlist rather on numerical analysis? It's somewhere, I think before partial differential equations even. Where is it now? Laplace. Yeah, I have numerical analysis. Yeah, 78 videos, starting from very simple things to very advanced things like partial differential equations like that. Okay, so that there you can find PDE methods. So the learning path, you can start with deterministic ODEs, then go to chaos and bifurcations, then study chaos, stochastic systems, look at network science, control theory, and research literature. Okay, so we have practice problems as usual. You want to check all of this out. Then you can use some of the codes I used. So consider the stochastic differential equation. Dx equals all this. So of course we have a noise component. Just simulate the system for different initial values. Investigate how noise affects long-term stability. Compare with the deterministic case. That is, the deterministic case is when you remove this. So you just have x dot equals x into 1 minus x. That's the deterministic case like that. Then compare it with when you add noise and see what happens. Then for noise-induced transition, you have these two. Then 3 and 4, you have delay-induced oscillations and delayed population model. So you can fix R to be 2 and vary the delay to see what happens. So you want to identify bifurcation points and all of that. So this is also similar when you talk about delay-induced oscillations. Then we have the Kuramoto synchronization threshold. So for the Kuramoto model, and then all of this, then you have the chimera-like states here. Consider two coupled populations, implement numerically and all that. Then for 7 and 8, now you have network consensus, you have epidemic spreading, like all of this. So consider SIS dynamics and all this. Then so you want to check all of this. Then 9 and 10, you have chaos control, network synchronization control, and all that, you know. Yeah, so try this out. Let's see how well this go. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you for doing that. If you have not subscribed, the question is, what exactly is stopping you from subscribing? Go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Um, Having done that, you can also become a member of the channel by clicking on join. That gives you a special privileges like getting to see some videos first, and or maybe only members get to see some videos. We can hang out together. We can discuss whatever interests you on my channel. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on there. Till I come your way again, keep doing maths right. Bye.